We can treat sales as some quantitative variable, so unit sales, cases, volume, dollar sales, whatever it is. And we get these nice linear demand curves that we've been using for 2 semesters almost in 580 and in this class. So
There's a smart train.
pretty. What's that?
There's a smart train.
Can you hear it all over here? I guess you can. All right.
Sorry.
I thought it was ocean liner or something. So here's our slopes and our intercepts and all that kind of good stuff. And promotion is a dummy, 0, 1. Increases promotion. Promotion is on, it increases sales. If it's on, if it's off, it doesn't increase sales. So it's a pure shifter. So we know how to handle these binaries, right? 0, 1s, as independent variables on kind of that side, on the right-hand side of our regression equation. We know how to handle them. They're shifters. We can interact them and change slopes. We can do all the stuff. We can do all kinds of stuff with dummy variables. What we haven't done is looked at a situation in which, it's just all stuff, where the dependent variable itself is a binary. So this, now we don't have a quantitative variable in terms of how much we purchase, but now we have a 0, 1 on whether or not you purchase. So this would be relevant for digital analytics, for example. Go to a website, did you buy or didn't? That's really all you have. We also have how much you bought, but one of the main issues you want to deal with in digital analytics is conversions. Can we convert a visitor to a purchase? It's that simple. So it's really a 0, 1 situation. Did you buy or did you not buy? Tasting rooms, right? You go into a tasting room, you visit, you taste. Did you buy or not? Did you not buy? So again, it's a binomial or a binary situation. And then we can have these independent variables that determine, well, which factors determine whether or not you bought. So who was it that does the big tasting survey every year? Silicon Valley Bank or Jesus, I did the data for them, the analytics for them. But they did this big survey of tasting rooms, things like whether or not what the tasting room fee is, whether or not they have a tasting room fee, what the tasting room fee was. Do you get the tasting room fee reimbursed if you make a purchase? Does that increase your probability of purchase? What are some of the other things that they had in there? They had location, so we looked at the differences in probability of purchasing between Napa and Sonoma. They had the price of wines. They had some I think they had some demographic data, but stuff like that. These are questions you can't answer with regular, ordinary least squares regression, stuff that we normally do. So lots of questions we can answer for these. Public policy questions, recidivism. I know, what's the probability that you end up back in jail? Cancer. I mean, it's just the number of uses for this kind of stuff is infinite, just as much as any other variable. But we can still have independent variables. So we got price here. The difference is, right, when we do ordinary least squares, if you were to Google regression, it would say, it's weird, how am I running this without my flashlight? I must have had it open already. All right, that's weird. If we were to do, if you were to Google or Wikipedia regression, it would be, curve fit. Let's find the straight line that best fits the data. It doesn't really work with binary data because the data is zeros and ones, and you either purchase or you don't purchase. So what ordinary least squares regression does is find the line that best fits the data. But it doesn't really make any sense. Again, you either purchase or don't purchase. And if the law of demand still holds, more purchases are going to be made when prices are lower than when prices are higher. So we're still going to use the same intuition in terms of the laws of demand, but we just have a different data set. We see fewer purchases occurring at the high price. So again, a very different look at the data. The scatter diagram, I think, illustrates the fact that we got a whole new set of data analytic tools that we're going to have to introduce to actually get some insights from this. Now, technically you can fit an ordinary least squares regression. We can run our normal regression in this data. And we'll get results. I don't know what those results are, but we'll get some results. We'll get a straight line, and we'll get the straight line that best fits the data, although that almost sounds counterintuitive because the line is a horrible fit. This is called the linear probability model. And it's got a fancy name, and it sounds really cool, the linear probability model. But it's a horrible, horrible model. It should never be used. Unfortunately, because of the difficulty of what we're going to do, and the ease of this, a lot of the times we're going to see, a lot of the times you see this linear probability model being used. But we can kind of gain some insights into this. So we run the regression, we get these output results. We still have similar interpretations of the betas. Beta 1 is still going to be a slope coefficient, the change in y resulting in a change in x, but now the delta y is interpreted differently. And it's interpreted as the change in the probability that y equals 1. Remember, y equals 1 in our simple case if you make a purchase, equals 0 if not. So now we're looking at, instead of how much more you buy when price goes down, now we're looking at what happens to the probability of you buying when the price goes down.
So it's just forcing a demand curve into the most likely price that it's going to be purchased at, and the most likely price it won't be purchased at.
Yeah, but I mean, look at that. To me, that's just a horrible, horrible picture. I can't emphasize how much I really dislike this. And it just bothers me. We interviewed a person, the last person we hired, one of the interviews did her PhD, and she used the linear probability model. It was at a good school, too, University of Santa Barbara, which is in economics one of the it's a top 20 school. It's a top-notch program, and I couldn't let it go. I had to stuff a glass of wine in my mouth. Something, tell myself to shut up, so I just let it go. We're not going to hire her. But yeah, it just didn't make any sense. Her committee should have said, look, you should have used some other model. So this goes from number of purchases to probability of purchase. So, and again, it's the same reg command. We're still going to reg purchase on price. We're going to get this output, but now this interpretation would be for every $1 increase in price, the probability of purchasing goes down by 0.1 percentage points. For every $1 decrease in price, the probability of purchase goes up by 0.1 percentage points. So you still have a similar interpretation, and I think that's why people like this, is because they can explain it, and it makes sense to them. But it should be, theoretically, it should be problematic. Mostly for a couple of reasons, but do you see any glaring problems with this? What would bother you about this? Remember, what we're talking about is the probability of purchasing. So
Like data points.
yeah, so we can do kind of the same analysis at a price of $5. Probability of purchase would be, and we can use the same equation, right? Take the coefficients, plug it in, get a probability of purchase of 74%. if you wanted these are the same kinds of questions we answered with regular demand curves. If you wanted a 60% probability of purchase, you can do the same thing. Go across, and you set the price at $6.40. So all the things we did with the regular demand curve, we can do with this linear probability demand curve. The problem is, one, it assumes a linear relationship, which may or may not be true. And I think more importantly, those two things. Probabilities are between 0 and 1. With a linear probability model, you can get a probability greater than 1, and you can get negative probabilities. So these are literally nonsensical results. And that's my main objection is, one, this relationship may not be linear, but I think more importantly is, I should put this as number one, is that you just get, you get probabilities greater than 1 and less than 0. The errors are supposed to be normally distributed. They're probably not. I'm not on video now. I'm being accused of porn. The error terms are going to be heteroscedastic. It's another violation of our assumptions. R-squared doesn't make any sense because, again, the data is clustered at 0s and 1s, so it's literally going to be a terrible fit. So it's not even appropriate to use in terms of finding the line that best fits the data. And again, it assumes that these probabilities stay the same, and they probably don't. So what we need is something that fixes all these potential errors. And that's going to be called the Probit model. This is where things get a little bit hairy. It's pretty simple. It's a pretty simple idea. It's based on the cumulative normal probability distribution. And we're all familiar with the normal distribution. Bell-shaped, centered at 0, standard deviation 1, blah, blah, blah. Pretty common. We use this for all of our hypothesis testing and our t-tests, and all that stuff comes from the normal, the standard normal distribution. So we're going to use this, and specifically we're going to use the density function, or here's the formula, for this to define our regression. So instead of finding the line that best fits the data, we're going to use this standard normal probability density function to define our curve, our fit. And we're going to use the standard normal cumulative density function, which is basically the sum of the probabilities of our standard normal distribution. And they're going to sum up to 1, right? The entire area under the curve sums to 1, and that's what's happening here. So we get this nice S-shaped curve. And the reason we're going to use this is that it's bounded. And again, mathematically, it's never going to go, as the probability of 1 goes to 0, it's never going to go below 0, and the probability is never going to go above 1. So we're either going to approach 0 or we're going to approach 1. So that's nice. So we're no longer going to potentially have nonsensical results. In other words, we're not going to have probabilities greater than 1 or probabilities less than 0. So we get these bounded regressions. And this is, even that in and of itself sounds impressive. Always positive, like probabilities should be. As x changes, the value of our cumulative standard normal distribution is going to change. So that's this thing. The main point is that as x changes, the value of the function changes. And notice that the standard normal probability distribution, top one, reaches its maximum when the z statistic is 0. And this is actually pretty important. Because we're going to call this, in the cumulative standard normal distribution, the borderline case. And it's the borderline case. In our S function, in our cumulative standard normal distribution, it's the point at which the curve goes from being convex to concave. It's that point of inflection in mathematics. And the reason that's important is because it's the point at which the probability goes from, well, at this point right here, the probability will be exactly 0.5, 50%. So we're going to call that the borderline case because, at least in our context, in the context of purchasing, you're on the borderline of whether or not to purchase. Do I purchase? You know, it's a 50-50 chance that you're going to purchase. So you're literally on that edge. Anything above that, and you're more likely to purchase, 51%. Anything below that, 49% and below, you're less likely to purchase. So we're going to call that the borderline case. And at that point, when z equals 0, at that point of inflection, the slope goes from being from increasing at an increasing rate to increasing at a decreasing rate. So at that point, the slope of the probit function is at its maximum. What is that? Well, the slope of a demand curve. The slope is the effect of our independent variables on our dependent variables. So if we have a steep slope, it means that consumers are insensitive. If we have a flat slope, it means that consumers are extremely sensitive. At that point, the slope of the probit function is at its steepest, which means that the effect of the independent variables are their greatest for that borderline case. Does that make sense? Black blank. So, and again, just kind of think back to our traditional demand curve. This is what I was saying that there's a lot of math, but it's really those curves that we need to understand. So we know, let's take a relatively, what we call inelastic. And I don't even like that word. Oops. Unresponsive. So what does that mean? It means that, here's Q0, here's P0. It means that if I raise price, consumers do what? They do very little. They buy less, the law of demand holds, but not much less. They're not very responsive. The independent variable doesn't have much of an effect. Price doesn't have much of an effect on how much we buy. We continue to buy at the same rate. So this is inelastic. If we are elastic, let's take this one, and this is elastic or responsive. Starting at that same P0, Q0, look what happens when we raise price. Now you have this huge effect. So the more responsive consumers are, really means the more effect that price or any of our other independent variables are going to have. It's the same thing here. What we're saying is that at that borderline case, at this point, the independent variables are going to have their biggest effect. So think of this intuitively. You walk into a store and you're literally on the fence of whether or not you're going to buy. You're trying to look for some reason to either buy or not buy. You're looking for some reason to make up your mind, right? So any little thing will have a big effect, right? So if the salesperson says, well, you're in luck today, we're having a 20% off sale, and boom, then it switches me from borderline to now I buy. And a good salesperson will kind of gonna see the people in the store and see, you know, whether or not they're a borderline case, whether or not they're deciding whether to buy something. Yeah, I kind of like it, right? If you're just sitting there staring at something for not years, for minutes, for hours, and you're really debating whether or not you should buy it, you're that borderline case. You either need a reason to push you over to that 51%, or you need to say, you know, to push you back down to the 49% or below. Something that's going to kick you over that fence so that you either buy or don't buy. So that's what we're saying. At that borderline case, the independent variables are going to have their biggest effect. And we'll see that. Yeah. We can see that kind of the opposite of that in the flat areas. So we know at the borderline case, the independent variables have their biggest effect. Yeah, you're equally likely to do that. You're flipping a coin, you're doing something else. Let's consider the opposite of the borderline case, the inframarginal case, where the opposite is true. The independent variables have very little effect on your decision to buy. And that would be at these corners. Remember, the slope represents the effect of the independent variables on the dependent variable, which is your probability of purchasing. It has its biggest effect here. What's the slope here? What's it close to? Zero, exactly. So that means literally, these people aren't going to buy. Fiddling around with price isn't, you know, or whatever the independent variables, fiddling around in this neighborhood isn't going to have much of an effect. You've made your decision, you're not going to buy, you're out of here. There's not a whole lot they're going to do to change your mind. Their minds are pretty much set up. The opposite is true over here. This person has a, and again, look at their probability of purchase is close to zero. The opposite is true over here. The slope is still zero, but their probability of purchase is really close to 1. So they're there, they're going to buy. There's not a whole lot you can do to get them to not buy. Hence, the independent variables have very little effect on their probability of purchase. So, and again, I was going to make fun of, you know, this is my wife shopping. It's insane. You know, we bought her car. It was, you know, she found the car she wanted and the color she wanted with the options she wanted. And the salesman's walking up, and I tell her, play it cool. Don't jump up and down. And so the salesman, you know, how do you like it? Just, it's exactly what I'm looking for. It's the exact color I want, and it's got the exact interior. Okay.
I would pay $5,000 over.
Exactly. So I knew right away, you know, there's going to be absolutely no bargain. Exactly. If she had played it, and by the way, I'm not any better than she is, so it's probably it'll. You know, if we had been over here, then, or if we had at least been over here, this is where they're starting to make their bargain. If they know we have no incentive to buy, then they don't even waste their time, right? They come out, they maybe say hi, and then they walk away 5 minutes later, or 5 seconds later. If they know we're here, this is where they start saying, and you've heard this before, oh, you just happened to hit it on the right day, or what was it? We're looking for a dresser for my daughter, and the salesperson asked, oh, when's your birthday? Oh, that's my birthday too. I really doubt if it was. I'll give you 20% off.
Let me see your license.
Yeah, exactly. I just heard you say that 5 times to the other people that were in here. You know, they're trying to push you from this borderline case to the other side. So, but just little things like that. You're trying to push people over. It's where the independent variables, the prices, and the other promotions and other things are going to have their biggest effect. In those flat areas, the independent variables are going to have their smallest effect. So when we're analyzing the things that we analyze, when we analyze price, we know where in the neighborhood where it's going to have its biggest effect. When we when we analyze promotion, we know where promotion is going to have its biggest effect. It's going to be probably closer to the borderlines than it is going to be to the extremes. And again, these make sense. And notice that unlike a linear demand curve, remember a linear demand curve, the slope of a demand curve is what? It's constant. It's literally constant. It doesn't change. That is, the effective price here has the same effect here, has the same effect here, and there. So on a linear demand curve, the effect of the independent variables are constant. They're everywhere the same. That's not true with these binary, or let's call them nonlinear demand curves, where the slope changes, and hence the effect of the independent variables is going to change. And that, to me, is a big improvement over the linear probability model, which I don't like to begin with. And that's probably one of the least reasons why I don't like it, but it's a big improvement on the linear probability model. Okay. So again, we're going to analyze price and promotion and all those things. So we want to kind of have an understanding of the shape. It's a bounded regression. It's always, the probabilities are always going to be between 0 and 1. We're always going to get this S-shaped probability. The slope changes. We know where the borderline case is, or at least we can identify where the borderline case is, and so on. Okay, so we just talked about this, these 2 points. All right. So here's the underlying theory. We saw the math. Stata's going to do all the math. But that math, as nasty as that math looked, it still gives us pretty complicated regression. So when we run a regression, when we run a probit, and this is a new command, we'll get, here's a demand curve, price, the probability of purchase. Notice it's S-shaped, but now it's going down. So it looks like a demand curve. It's downward sloping, so it's following the law of demand. It's always negative. And now we get this wacky looking output. And this is where things get hairy. It's a different methodology than ordinary least squares regression. This is literally a formula. If you could see the formula, it's literally just a mathematical formula that finds the line that best fits the data, minimizes the sum of the squared error, all that kind of stuff. This is an iterative process. And iterative is a fancy name for trial and error. It's guessing at different coefficients here. So notice, it's got these iterations. So in this one, it went pretty fast. It converged after 5 iterations, so 0, 1, 2, 3, and 4. But there can be models, and we'll come across models that will take a little bit longer to iterate, to converge. So we get kind of a similar output, but there is a lot of different stuff in here. Let's see. Yeah, this data shows the number of iterations it takes to converge to a solution. And what's happening is this is called maximum likelihood. So essentially it takes the log of some likelihood function and it tries to find the coefficients that maximizes it, and not the function itself. So it's a whole different estimation process. The first iteration, iteration 0, is called the null or empty model, and it's essentially running instead of running probability y equals 1, beta 0 plus beta 1 price. Instead of running that, it basically runs one without any independent variables, and that's called the null model. And essentially what it does is it starts adding the independent variables and to see what happens to the likelihood function. So again, it's called maximum likelihood. So what that means is it finds the coefficients that maximize the likelihood that they came from the data. Again, it's just a different estimation process. But it starts with this empty model or this null model, and then it tries different coefficients and adds the independent variables. The log likelihood function is negative because the likelihood itself is always between 0 and 1, so we're taking the log of that, so we get a negative number. And that's, yeah, you can see the log likelihood numbers, the actual numbers themselves negative 967, and so on. The next iteration is called iteration 1, and that's where the independent variables are included. And each iteration, we're supposed to get closer and closer to the maximum likelihood. When the iterations get close enough to each other, then that's when they converge, and that's when the iteration stops. So if you look at the last two iterations, negative 822, 28494, negative 822, 28494. So it looks like the log likelihoods aren't getting any better, and that's when it stops. That's when it converges. If we carried these out a few more decimals, we probably see that there is some difference. And when that difference gets small enough, when the log likelihood between those two iterations gets small enough, then that's when the iterating stops and it's said that the model has converged. And the data we're going to use, at least initially, are going to be, they'll converge fairly quickly. Maybe longer than this, but somewhat quick. Yeah, so those are those there. And that's going to be the maximum, which is that number there. So again, different output than our ordinary least squares regression. All right, what else is in here that we don't know, that we've never seen? Circle. The likelihood ratio chi-squared statistic, that thing there. That is equivalent to what we used as an F statistic. Remember, an F statistic was used for hypothesis testing, and this is really used similar to that. The probability for the chi-squared statistic is similar to the probability for our F statistic in our regular regression. All right, so essentially what the likelihood ratio test says is if we assume all the independent variables are 0, we run that regression, and we compare it to a regression in which at least one of the independent variables is non-zero, is the likelihood ratio statistic any different? So it's a kind of a formal hypothesis test, and that gives you that LR chi2 statistic. And the next one below that is called a pseudo R squared. Remember, R squared really doesn't make any sense because fitting a line really doesn't make much sense. We know the fit's going to be bad. So in essence, they've come up with these pseudo R squareds. And there are probably 20 different pseudo R squareds. The one that Stata uses is called the McFadden R squared. McFadden, I think, is still at Berkeley, won the Nobel Prize for his work in this area. So it's a pretty common measure of fit. Although, again,